cycle is a series of reactions, a pathway, that is the fixing of carbon dioxide into sugars. Not into glucose, but into a sugar called G3P, glyceraldehyde 3-phosphate, which can go on to another pathway to make glucose and starch and cellulose. This is really the basis of all life on this planet, because pretty much all of the energy coming from the sun is captured through photosynthesis, and this reaction is central to that and to making larger organic compounds. The cycle was figured out by a guy by the name of Melvin Kelvin. How would you like to have that for a handle? Melvin Kelvin. A name like that, you're destined to be a nerdy scientist, I think. He actually was using algae, very large type of algae called chlorella, and he was growing that in vats of water. And he introduced carbon-14 into CO2. So he made carbon-14 CO2, radioactive CO2, and he would introduce that to the algae for like very brief moments of time, for like fractions of a second. And that CO2 would get very quickly taken up and basically would get incorporated into the different molecules here. And he would, give it just a brief flash of that radioactive CO2, and then he'd plunge the entire vat into boiling alcohol, which stopped all enzymatic reactions and fixed the carbon-14 in whatever molecule he had it in. And so he would do decreasingly short or decreasing time periods. So, maybe he did a minute, and then 30 seconds, 30 seconds, and 10 seconds, and then, down to fractions of a second, so that he could get the first stable compound he could identify with the radioactive carbon dioxide, where it got incorporated into. The first compound he could find was a 3-carbon compound that turned out to be 3-phosphoglycerate. So this is sometimes referred to as C3 for carbon-3 photosynthesis. So C3 photosynthesis because the first stable molecule that could be identified is a 3-carbon molecule. Okay. So kind of a clever way of how to do this. I don't know if you guys know my wife, but she also worked with radioactive CO2 with fruit flies real briefly, which was fine until she accidentally let them out, and then all these radioactive fruit flies would fly. Which was a bit of a hazard problem. She asked her about this. I always like to bring up embarrassing things that ask me about. It's good for the marriage. All right. So there's a couple of things about this. It's not even Friday. It feels like Friday.
It does.
Everybody gets goofier on Fridays. All right. So this figure's got a couple of things that are a little confusing. So it's done in threes. So there's 3 CO2 entry. Okay. It's kind of arbitrary that they chose to do 3 CO2s entering. They chose 3 CO2s entering instead of 1 CO2 entering because they want to take 1 G3P out of the cycle. Okay. The reason it's in threes is so they can take 1 G3P out. So you have to have 3 carbon dioxides enter the cycle before you can have 1 glyceraldehyde 3-phosphate leave it. The stoichiometry on this is precise. So you start off with, well, let's start here with the ribulose bisphosphate. You have 3 molecules of ribulose bisphosphate, which is a 5-carbon compound. So that's 15 carbons. Okay. You add 3 CO2s, and now you've got 3. Well, let's go to this one. You've got 6 3-phosphoglycerates. That's 18 carbons, right? So 15, you add 3, now you've got 18 carbons. Okay? You stay with 18 carbons until you kick out 1 G3P, then you're back to 15 carbons with 5 G3Ps. Okay? So everything is for 3. Okay? So for 3 CO2 entering, you're going to need 6 ATP here and another 3 ATP here, so that's 9 ATP from the light reactions, and you'll need 6 NADPHs from the light reactions. If you do it per carbon dioxide, which is how I think about it. So I think about how much ATP and NADPH do I need per carbon dioxide. You would need 3 ATP per carbon dioxide and 2 NADPHs per carbon dioxide. If you can memorize that, any question I give you, I could ask you how much do you need for 6 or for 24 or whatever number, you can use multiply it times how much you need.
2.
Right, so for 1 CO2, you're going to need 3 ATP and 2 NADPHs.
So then you technically get a third of G3P leaving in that ratio? You're a third of the way there to get 1.
When you say a third, do you mean based on 18 carbons or 15 carbons? I don't usually think about it that way. For every 3 that enter, you can have 1 molecule of G3P.
So you're not thinking about the G3P leaving when you think about it like that? Because it takes 3 CO2 to get 1 G3P to leave.
Yes.
And so for 1 CO2, you can't even get it, so you don't.
Correct. You're right. You're going to need to have at least 3 enter before you can get 1 G3P. All right. What's the ATP do? Well, let's go over the phases. So there's 3 phases to this cycle. So you should know the first reaction. The first reaction is RUBP, and you can do the abbreviated part, right? You don't have to write it all out, but RUBP plus CO2, so CO2 plus RUBP, using the enzyme Rubisco gives you a 3-phosphoglycerate. There's a 6-carbon compound, but it's very brief. It quickly breaks into 2 3-phosphoglycerates. Okay? Both of those 3-phosphoglycerates have an ATP added to them to become this compound 1,3-BPG, which is 1,3-bisphosphoglycerate. And the first reaction in here where the CO2 is added is the carbon fixation part of the phase. Right? So this, in the carbon fixation part of the phase, that's where CO2 is fixed. Okay? The second phase is called the reduction part of the phase, and that's where the NADPH is oxidized and the 1,3-bisphosphoglycerate is reduced to G3P. That's the reduction part, where the electrons are transferred. And then the third part is the regeneration phase, and that's where the G3P is converted back to RUBP. And there's about 20 reactions in these things that aren't shown. So it's actually pretty complicated how to get it back. But basically, to get back to this RUBP to keep the cycle going, some of the G3P has to be rearranged into phosphate. So things you need to know. You need to know each of the 3 phases. So if I ask what happens in the carbon fixation phase, that's where the Rubisco adds CO2 to RUBP. If I say what happens in the reduction part of the cycle, that's where the NADPH gives its electrons to make G3P, glycerol 2-phosphate. If I say what's the output is G3P. If I say what's the regeneration phase, that's where the G3P gets converted back to RUBP. You should also know how much ATP and NADPH are needed for this per CO2 or for 3 carbons or for 6 carbons, whatever. If you know how much for 1 CO2, you can calculate anything that I ask. In terms of actual compounds you should know G3P, you should know RUBP, CO2, you should know Rubisco. And if you know these other ones, that's great. Actually, you should probably know the 3PG, so if you know that first reaction. That's probably the minimum you should know, and you should be good. All right. Questions on any of this? I'm trying to think what I forgot to say. So for every 3 CO2s, 1 G3P exits. If you have 5, in this example, if you have 5 G3Ps, that will get rearranged into 3 5-carbon RUBPs, just so the carbon stoichiometry stays the same. And for 1 CO2, you need 3 ATP